Hi, I'm Dave Lewis. I'm Chief Data Scientist of BrainSpace, and I'm going to be talking about the use of supervised machine learning in BrainSpace's text analytics software. Okay, so we've all seen slides like this. The amount of data is growing exponentially, gets worse all the time, and in particular, unstructured data is growing exponentially. What's the trouble with unstructured data? After all, Amazon doesn't have a problem if they get 10 times as many purchase transactions. They can add up that amount of money without any trouble. The problem with text, with unstructured data, is you can't do anything with it. You can't average it. You can't add it up. You can't graph it. And you certainly can't look at all of it. And that's where machine learning comes in. So BrainSpace uses a bunch of different machine learning technologies, but they fall into two major classes. Unsupervised learning is where a machine learning algorithm goes out and it finds structure on its own. So for instance, BrainSpace has a clustering algorithm which organizes documents into groups and presents them through a powerful user interface. It automatically uses latent analysis to detect relationships between words and phrases. Those are very powerful technologies, but today I want to focus on the other major form of machine learning, which is supervised machine learning. And in supervised machine learning, you have some structure that you have in mind, and you want the algorithm to learn to impose that structure on the data. So the user then is the supervisor, the guiding of the algorithm to find the structure that's desirable. And I'm going to talk in particular about a particularly simple type of supervised learning, which is learning of a binary classifier. And all a binary classifier is a rule that sorts documents into two groups. If you can sort the documents into the interesting documents and the non-interesting documents, the supervised machine learning algorithm will learn to imitate your decisions, create a rule that can also sort those documents into those groups with some degree of accuracy. Okay, so a little more complicated than that. What the supervised learning algorithm actually does is produce what we call a predictive model. The predictive model takes a document in, and if the document's likely to be in the interesting class, it gives it a high score. If it's likely to be in the uninteresting class, it gives you a low score. And then you can decide how high a score is high enough to be good, and you could set a cutoff on that. And typically then the binary classifier has those two parts, the predictive model produced by the supervised learning algorithm, the cutoff that's produced by you, the user. And we'll see the use of both of those things in the tutorial. Okay, so this is BrainSpace. I've loaded here a collection of about 1 million emails that were publicly released from the Enron Corporation. Let's say we're interested in whether Enron employees were participating in fantasy sports competitions, gambling on sporting events, and so on. There's a lot of different vocabulary that would be involved to find those documents, names of different sports, teams, kinds of wagers, etc. So this would be very hard to write a keyword query for. Instead, we'll teach the software by example to recognize these messages. So let's click on the supervised learning functionality. And we're going to create a classifier for this topic. So we'll just call it, say, sports betting. And we'll define the positive and the negative categories for that. All right, and here's the CAML interface for continuous multimodal learning, one of the two supervised learning capabilities in BrainSpace. And this is the one that I'll be focusing on for this lecture. Okay, so to do supervised learning, we need some training documents. Let's just do a search for the topic we're interested in. So if we type in sports gambling, we'll also get to see one of the unsupervised learning capabilities of BrainSpace, which is our conceptual search. And it has run a latent space analysis algorithm to find related terms. So we see we've expanded sports gambling with things like bets and gambling and winners and whatnot. We can look at the top ranked documents over here and we'll say, okay, this one is about gambling, but it's not about sports. So we're actually going to mark that as a no. Next one is about gambling on sports, so that's going to be a yes. Next one also is about gambling on sports, so that'll be a yes. And this one also is some sort of either a fantasy sports tournament in this case. That one will be another yes. So we've got a few examples of me as a human being making classification decisions. Let's have the supervised learning algorithm see what it can do with that. So we'll go back to the camel screen and we'll click Train Now. Okay, so what happened when we hit Train Now? We train a predictive model. The supervised learning algorithm looks at all the documents that we coded, builds that predictive model. Then the software runs that predictive model on all the million documents in the database, gives each of them a predictive score, and we index that predictive score as a new attribute of the documents. So we've used machine learning to create new metadata associated with each document. Okay, so let's go back and look at what we learned. So let's see what training produced for us. We just trained off of these two documents, one positive and one negative. But we can see when we look over to the side, we've got a bunch of sports documents up at the top. So we're already in a good state here. Let's click on the top and we'll see the Zen mode. So when you're at the CMML screen, you can go to the ranking of documents that's produced by the current predictive model, and you can just start tagging those documents. So this document at the top is a relevant example. This one is a relevant example. Look down here, yep, this is another fantasy sports. And we can sort of go very quickly from the top of the ranking downward, tagging documents with one click. And that makes it very efficient then to tag large amounts of training data. So you can see we've already gone through 10 or so examples just from as I've been talking. All right, so we were able to tag a number of examples very quickly. If we go back to the CMML screen, we can see that we've got 7 more examples. We could hit Train Now, and it will build another classifier. And typically, when you're doing supervised learning, you'll go through a number of training rounds, and you might train several hundred examples to get a predictive model that would be highly effective, but you can do it very quickly because of the responsive graphical interface. Just to save time here, I will go to a classifier that I'd already created. So here's one where I already have tagged a few hundred documents, again for the sports betting topic. We've now got a bunch of labeled, some additional labeled examples, and I've actually just, for simplicity, already run the training on them. And so what that shows is the value of the predictive model in choosing training data that can then improve the predictive model further. That's called active learning. All right, so we've seen how the predictive model can be used to identify some pretty good training documents. These top-ranked documents were largely relevant. It turns out there's even better training documents that the predictive model can identify, and that's the ones that the model itself is uncertain about. It's not sure whether they're in the target class or not. BrainSpace incorporates a very sophisticated active learning method that identifies documents that are uncertain in this way, also identifies documents which are different from each other because that's valuable for training, and identifies documents that will help classify a lot of other documents in the database. By taking all 3 factors together, you can get as good a predictive model from a training set of a few hundred documents than if you'd selected tens of thousands of documents at random and spent weeks coding them. Okay, so I mentioned that BrainSpace has more advanced forms of active learning, and we trigger those very simply. We'll just click on New Training Round. There's a bunch of different ways you can choose training batches here, but we have our diverse active learning algorithm and then a faster version for very large databases called Fast Active. We can say, let's say we wanted to do a batch of 50 documents, for instance. We would just do that. And BrainSpace will go out, identify a batch of 50 documents, and then give us the ability to review them again efficiently, very similar to Zen mode. It's also possible to review the batches of documents in other review platforms that BrainSpace can connect to. So we've talked about using scores. Let's talk about using classification. The simplest way to do classification is with the trim control. One way we can do that is just enter a document count. So we could say, we want, say, the top 10,000 documents based on the predictive model score. Or we can set a cutoff. We can say we want all of the documents that have, say, a score of 0.7 or higher. Either of those things takes the scores from the predictive model and produces a yes-no decision, either yes-no because you're in the top 10,000 or not, or yes-no because you've got a score of 0.7 or not. And so we can then take those yes-no decisions and say, we're going to put all the yeses into a notebook, just a set of documents you can pass on to some other kind of processing. Or we can put all those documents into a focus, which is a sub-collection. And I'll talk a little more about sub-collections and how you can do analytics on those in particular. You can also tag documents that are above the cutoff. So those are all sort of ways that we begin to go from scores to classifications. All right, so we've seen how the scores produced by a predictive model can be used to rank documents, used to select good training examples, but we can do even more if we convert that score into a yes-no decision using the user-specified cutoff. Because then we have sort of the perfect database attribute for your problem. We have interesting documents and not interesting documents. You can combine that attribute with other attributes in the database, other metadata, other query operators to form very powerful queries. So let's look at a bunch of examples of that. Okay, so let's see what we can do with classifications. We now have an attribute which corresponds to this sports betting topic that we're interested in. Let's combine it with other things. So for instance, maybe we're mostly interested in documents from the year 2001. So we can click on that. BrainSpace has a graphical interface which lets you easily do time-based queries. And then now let's combine that with our classifier that we created. So we'll look up that classification. Okay, and we'll say let's have documents that have a score of, say, 0.5 or more. And so now we're getting the documents from 2001 that our trained classifier says are about sports betting. And if we look over here, we say, sure enough, they are. And so, let's step back and think about sort of the power of what we've done there. We're now doing a query on a database attribute that didn't occur 10 minutes ago, and which corresponds to exactly the topic that you're interested in for your investigation or study. Okay, so we've seen how powerful it is to be able to refer to classifier scores as part of a database query that also makes use of other attributes. But maybe we don't want to have to sort of type that clause testing on scores every time. What we can instead do in BrainSpace is take a classifier and create a sub-collection or a focus that contains only the documents that have high scores on that classifier. Then every query we run subsequently on that focus will implicitly be taking advantage of the fact that the classifier has found the most interesting documents. So let's see how that works in BrainSpace. Okay, so let's take a look at a focus built from the top 10,000 sports betting documents. We can see that the statistics on the dashboard are limited to just those 10,000 documents. We can take a look at the cluster wheel, so we can browse those documents and see that we've got various subsets, fantasy sports, things like that. And then also, instead of having to type in a restriction on the scores of documents every time we do a query, we can just do a query on the things we're interested in. So for instance, let's say that we're interested in documents about this guy. So we'll just add their name to the search, and then we'll have the top scoring documents about sports betting from this particular custodian. We also could say, let's say that, well, we've built this classifier for sports betting, but we notice most of the documents are about football, and maybe we're interested in basketball instead. Well, that's fine. We can just type in basketball as a keyword. Okay. And then when we search, again, we're going to be searching basketball documents, but we're going to be searching basketball documents that had high scores on sports betting. And so we can see that even though most of the sports betting documents are about football, we can restrict with the keyword basketball and get just the ones that are about basketball. So it's incredibly powerful to be able to take this topic that we're interested in, turn it into a metadata feature, and be able to combine it with all sorts of other query attributes. Okay, we've seen that if you've got a good classifier, you can create a sub-collection or focus from it. Suppose you've got a good sub-collection or focus, it can actually be useful to restrict supervised learning to just that focus. One reason is maybe you've got all the good stuff in there. Also, the smaller the set of data you're operating on, the faster things run. And it also turns out statistically that you need less training data the smaller the sub-collection is. Finally, we may have multiple sub-collections of interesting documents that we're interested in. For instance, we might be looking at both sales and engineering documents in an investigation, and it may be that the interesting documents are just different in those two sets, and it's worth building different classifiers for them. Or we may have a mixture of documents in multiple languages, say English and Spanish. While you can apply supervised learning to a mixture of documents from multiple languages, there can be some advantages to building a separate classifier in each language. So in fact, let's look at what that looks like in BrainSpace. So this is a classifier I've created on a focus that was built from just the Spanish language documents in the Enron corpus. There's only about 300 of those out of 1 million, but we've identified them with BrainSpace's language identification capability. And then I've built a predictive model just on those Spanish language documents. Would be appropriate for classifying those documents, might not be appropriate for classifying English documents. And we can see it's doing something sensible with ranking the relevant documents at the top. Okay, so far we've been talking about predictive models and classifiers as black boxes. You put documents in, you get a score or a decision out. But it can be useful to look inside that black box. BrainSpace has put a lot of effort into both natural language processing in a bunch of languages and machine learning in order to make the predictive models we learn interpretable. And we call these portable models. You can take a model that you've trained from data and export it. You can look at it in a spreadsheet. You can use it in a new data set. And you can generally get value out of that for future projects. You can even create a portable model by hand, and it's really nothing more than a spreadsheet with a list of words and phrases and numbers associated with them. You can then use that portable model to start off training, update it with supervised learning on a particular data set, and improve it. So you're not starting from scratch then on a project. You actually already are in a very good position with a model that you've created by hand using your domain knowledge. You also can look at how that changed over time, where you started from and where training took you, in order to get a sense again of how was the topic different maybe than you thought it was at the beginning. So let's take a look at that capability for comparing models, which we call model insights. Okay, so let's look at model insights. So here's another version of the sports betting classifier. In this case, I started it out with a set of good terms that I had in mind were appropriate for sports betting, and then I did a bunch of training just like in the other examples we looked at. So let's open Model Insights and compare the original terms I had. So I'm going to go to round 1, and I'm going to bring up the original terms that I had. Okay, so I had put in things like wager, pool, odds, gambling, and whatnot. And we can see their original rank in the list of the portable model that I created by hand. And then we can see what their rank is after we've trained on a few hundred examples. So we see things like, wager and pool were pretty good terms. I had them as my first and second terms. They're now like ranked 5 and 6. And then other terms that I thought were good, like fantasy for fantasy sports, actually is only the 200th best term. And sports itself is only also like down around 200 or so. So some of the terms that were in my portable model were very good, some of them weren't. And so I've learned more about what is a good term for the topic in this data set. And then if I add in the new terms, and I see what the top ranking terms are now, I see horse racing is actually a very powerful term. We also have some other kind of weird terms. What's this stuff? Well, there was a bunch of URLs from all this bulk email on sports gambling. Those get broken up into pieces, and they're very distinctive. Everything that came from a URL from this particular company was about sports betting, but it's not something that you would obviously think about, because until you saw the data, you wouldn't have known that this particular URL had this particular structure. So this is an example of some of the kinds of things that you see when you start looking at the actual classifier that was built. We also have a bunch of names of people who were involved in fantasy sports or sports betting, and a bunch of other terms. And so beyond simply accurate predictions, accurate classifications, you also get insights into what is distinctive in this particular data set about the documents you're interested in. All right, so we've seen how supervised learning builds predictive models by learning from user classification decisions. And predictive models impose structure on text data. They can act as a kind of supercharged search. They can be combined. Classification decisions then can be combined with other database queries. They can identify sets of documents for focused analytics, or can be applied to important sets of documents you've already identified. And then finally, the models themselves give insight into the documents that are important to your project by looking at what characteristics identify the most important documents. So very powerful technology in supervised learning. Thanks for watching this lecture on supervised learning. I'm Dave Lewis, Chief Data Scientist at BrainSpace. If you'd like to learn more about supervised learning or learn more about anything in BrainSpace, please contact us at sales@brainspace.com.